right, this is Math 2, Lesson 9.3.1, Average Rate of Change and Projectile Motion. So this is there's a lot here, but it's also fairly straightforward. So we'll see how it goes. You have calculated the speed of a moving object by dividing the distance traveled by the time, because that's what speed is, distance divided by time. For example, if you drive a distance of 150 miles in a total of 3 hours, then your average speed is 150 miles divided by 3 hours, or 50 miles per hour. However, what if an object is not traveling at a constant speed? How can you determine the speed at any given point in time when the speed is increasing or decreasing? So, Sasha used video footage from the water balloon contest, if you remember way back to chapter 5 when we did the water balloon contest, to record the approximate at specific times of Maggie's balloon. Her data is shown on the table at the right. Maggie's balloon reached a maximum height of 90.75 feet. How quickly did her balloon rise and fall? At what times is the balloon's velocity or speed different? What was the balloon's velocity or speed during different times of its flight? Complete the parts below to answer these questions. So the first thing it told us to do, which I deleted, was to plot all our points. So I did that for us. And then it says we should probably try to connect our dots. So we'll do our best to connect the dots in a smooth curve, if possible. We know it goes up a little bit higher than this one. Then it clearly starts coming back down. And probably hits the ground around 5 seconds somewhere. So something like that. Okay, this is what you expected to see as she launches her water balloon. Okay, so that's the idea, your basic thoughts. Pretty straightforward. Average rate of change is calculated by determining the slope between 2 points on a graph, because rate of change is, the change between 2 points, so average rate of change is the same thing. For example, if we calculate the average rate of change between these 2 seconds, write your answer with units, and then we'll look at the next question. So the change in height divided by the change in time. So at 1 second, it was at 60.3. I'll do this over here. 60.3 at 1 second, and at 5.5 seconds, it was at 34.2. And then we're going to divide by 1 minus 0.5. Okay, and so I'm going to let my calculator do that for me. 60.3 minus 34.2 is 26.2. I did not mean to turn that on. So 26.2 on the top, the bottom is 0.5. Make it a fraction. Nope, not that. Divided, 26.2.1, excuse me, I wrote that wrong. Divided by 0.5 is 52.2. So, write the answer with our units. It's 52.2 feet per second. What does this mean in the context of the balloon launch? So since this is rate of change is velocity, it means, since we're going between here and here, that the average velocity or speed at which the balloon was launched might have been 52 feet per second. That's what it means. Okay, choose another 2 points and choose 2 points to calculate the approximate velocity at 1.75. So when we do this, we actually find the velocity in between, or like at the point directly in the middle of those two, just so you know. So if we want to do 1.75, once this 175, I'm going to go ahead and give myself some more space. So if we want to, I need this back down a little bit. Okay. 1.75, I'm going to be doing these 2 points here. Go around 1.75. Seriously, pen. There we go. And so that'll be 88.4 minus 78.4. Hey, I can do that without a calculator. That's 10. Divided by 2 minus 1.5, which is 0.5, is 50 feet per second. So it's slowing down. So as it gets higher, since the velocity has decreased, it appears to be slowing down. slowing down because, and we don't really know, by the way, it's a calculus question, slowing down because the velocity is decreasing. So the velocity was 52 and now it's 50, so it's slowing down. Okay, basic idea. Let's see what we can do next. I'm probably going to need, I'm going to actually grab that. All right, so I went ahead and grabbed the table so it would be on the page with me. You wouldn't need to do that because you have it on your paper. So Maggie's balloon landed after approximately 4.8 seconds. When did it reach its maximum height? Choose a point of points and calculate the approximate velocity of the balloon just after it reached its maximum height. So if you recall, we have our picture here, which I also grabbed. It must have reached its maximum height somewhere around here. And I'm going to say either in between these 2 points or right after them, because its maximum height was, it says up here, well, not up there, it said in our words, 90.75 feet. And since the largest in our table is 90.5, it was either on its way back down or on its way up. One of the two. Okay. So that's not what I intended to do. So let's go ahead and we're going to use, let's use it on its path up, and we can also use its path down and then kind of put them together. Yeah, just after it reaches its maximum height. 4.8. I'm going to say it's on its way down right here. I'm going to use these two. And the reason being is if it took 4.8 seconds to land on the ground, its maximum height was reached directly in the middle of that, and that would be 2.4, and so this is right after it's on its way back down. That should be 2 words. Not taught. 2 max. Okay, so I'm going to use those two. So I'll have 90.5 minus 88.4 all over 2.5 minus 2. And again, calculating, using the calculator to get those numbers. 90.5 minus 88.4 is 2.1 divided by 0.5. Which is 4.2. Okay, again, feet per second. So it really slowed down, really slowed down. What happened to the velocity of the balloon just before and just after it reached its maximum height? So it's like going like this, and so what happened to the velocity just before and just after it reached maximum height? So what's happening is it's slowing down and then it's holding still. And so it's at its max height, the velocity is 0, which is crazy because that's why it turns around. It has no more momentum to keep going up. And so as I come down, the velocity actually becomes negative. So because velocity is speed with direction. So when it's positive, it's going up. And when it's negative, it's coming back down. So if we'd done these two numbers, it would actually be negative because I'd be subtracting. This goes first, that goes second. It would be negative every time. So right before it, so as it starts to come back down, it becomes negative. So does that make sense? This was just before. If I did just after, I'd get a negative number. What do you predict the velocity to be just before it hits the ground? And just before it hits the ground, it's going to be going much faster. It will be, so it was 52 half a second after it was launched. That's the one we did. And if I did, this is 52, and so it will be like 55 feet per second. And let's go ahead and calculate that right before it hits the ground. So it's going to be it's going to be negative though. 18.8 minus 48.8, which I think is 30. Yep, 30 over 4.5 minus 4, which is 0.5, which is negative 60. So it's off a little bit, but it gets faster as it comes back down. And again, the sign on velocity has nothing to do with slow and fast. If it's positive velocity, it's moving away from, and if it's negative velocity, it's moving towards. When we talk about with objects that are leaving the ground, it's moving away from the ground, but it's moving towards the ground. And that's all that positive and negative means. That's just the direction, okay? And so that's that. Let's take a look at the next set of problems. Sasha has a graph from Jen's balloon launch and knows that Jen's balloon reached a maximum height of and landed approximately after 4.9. She made a new graph with time in seconds on the x-axis and the height of the balloon on the y-axis. Use this graph to estimate their average rate of change when 2 seconds, 2.54, and 1, and 0.1. And so to estimate the average rate of change at 2 seconds. So here's 2. So that's, this is 1. What are they counting by? 0.75? Yeah, so that is 2. No, 0.5? I don't know what they're counting by. Divided by 6.25. That's weird. Okay, anyway, whatever. We should have made a better graph, but anyway. I could pick any 2 points around 2 seconds. Like this one's nice, and that's nice, and I could find the average. So that's kind of the idea. 2.5 would be here, and it looks like I should get 0. If I choose these two, I will. It's kind of like making a little sloped line. See? That's the idea. We're just kind of straightening it out for a split second. We're going to skip this one. All right, Sasha used the timestamp on her video to determine that Al's balloon landed after 4.5 seconds from the competition data. She knows that Al's balloon reached a height of 81 feet, which is 27 yards. Write the equation of a function that shows the height of Al's balloon as a function of time. Okay. All right. So it landed at 4.5 seconds. That means it reached its maximum height halfway in between at 2.25 seconds max height, which was 81 feet. So that's our vertex. So we know it's y equals sum a, x minus 2.25 squared plus 81. We just need to figure out what a is, knowing that when at 4.5 seconds it's at 0. So I'm going to get 2.25 squared when I plug in 4.5 plus 81. And a's got to be a negative number because this has got to equal 0. So let's see what's going on. We get 81 equals 2.25 squared is 5.0625. 81 divided by 5.0625 is 16. Well, that's nice. Except for that a should be negative. I don't know why it didn't come out negative. because it has to be because it's opening down. Let's make it negative. So my equation is y equals negative 16, which makes complete sense to me. X minus 2.25 squared plus 81. That's my equation. So after this video, also kept with Charlotte trying to win. He, by stealing a slingshot and launching a water balloon from the top of the bleachers 15 feet high, write an equation for Charlotte. Remember that he is using Al's slingshot, which means it should be very similar in how long it takes it to rise and fall. But he started higher. And so, let me think about that for a minute. All right, so since he stole Al's slingshot, the idea is to take Al's equation and add the initial change in how high it is. So it's going to, the vertex will be up 15 feet higher. So 81 plus 15 is 96. Okay, and so there's his equation. For what time period is the height, is it increasing and when is it decreasing? So it's increasing until it reaches its vertex, and it's decreasing after that. So it'll reach its vertex at 2.25 seconds in. So it's increasing from 0 to 2.25. And decreasing from 2.25 to when it hits the ground. And it should hit the ground in a similar time frame, but I'm going to go with 5 seconds ish. It's a guess. Okay, whenever it hits the ground. Whatever that number is. Okay. All right, quadratic functions are useful. The general equation is, in this equation, A is an acceleration due to gravity, while V is the initial velocity with which it was launched. H is the initial height, and T is the initial time. Al's equation, write Char's equation. So Al's equation was y equals, which one was Al? 81, okay. Y equals negative 16 parentheses x minus 2.25 squared plus 81. And then Char's equation, I'll do down here in blue, is y equals negative 16 parentheses x minus 2.25 squared plus 96. Then we're just going to manipulate them. So I'm going to need to multiply this guy out. We'll do that over here. X minus 2.25. X minus 2.25 will become x squared minus 2.25x twice. So 2.25 plus 2.25 is 4.5 x, and then 2.25 times 2.25, or 2.25 squared, is plus 5.0625. Okay, so that's this stuff squared. So I'm going to have negative 16 times that equation, expression. Then we need to distribute. So we got negative 16x squared plus 72 5.0625 times 16, 81, so that should be negative, plus 81, which is equal to negative 16x squared plus 72. Now, the only thing that's going to be different here, I'm going to get the same thing until I add. So I'm just going to still this line, that stuff, because it's going to be the same, equals negative 16x squared plus 72x x minus 81, now plus 96 instead, which should change very little, except for that negative 16 should still be there. Negative 16x squared plus 72, that should have an x next to it. 72x plus 15, and that's his initial height he added. Okay, so his initial height, what do the coefficients represent? So that's all the stuff up here. So A is negative 16, and it represents acceleration due to gravity. And B, 72, is the initial velocity. And there you go. All right. Have a great day. See you guys soon.